Hi everybody, so we are in section 4.3, looking at continuing to talk about the uses of the derivative. So last time we talked about how to determine local maxes and min values. Today we're going to be looking at global maxima and minima. So we say for any function f has a global, also known as an absolute minimum at p if f of p is less than or equal to all values of f, and we say f has a global or absolute maximum at p if f of p is greater than or equal to all values of f. So in terms of their definitions, the local maxes and mins and the global maxes and mins are defined very similarly. So a global or absolute minimum means that this point is less than or equal to all values of f. So when we were talking about local minima, that meant it was the smallest thing in its immediate vicinity, right? Just everything around it. A global minimum is smaller than everything else. It is the absolute smallest value on the entire function. Similarly, the absolute or the global maximum at f of p is greater than or equal to all values of f. So that means the global maximum is bigger than any other value on the entire function, not just one small piece of it. Okay, so we're going to look at some different scenarios here dealing with these max and min values. So to find the global maxima and minima of a continuous function on an interval, including endpoints, compare output values at all the critical points in the interval and at the endpoints. So that's going to be a big thing for us. We're going to compare output values at the critical points and the endpoints. So basically we're going to find where all the possible local maxes and mins are. We're going to look at their outputs. We're going to also look at the endpoints, and then we're going to make our determination from there. So if we just create a graph here, so just put one right here, something like that. Okay, we'll just pretend this looks a little bit nicer. But we'll go from A to B. Okay. And then when we're trying to identify these maxes and mins, well, I can see right here, at that point, that looks like a local min, that looks like a local max, that looks like a local min. All right, so we have a local max, we have a local min, and over here we have another local min. Now we can compare these values with the outputs at the endpoints as well. So we're also going to compare at the endpoints up here. So if we look at their outputs, notice the absolute lowest value on this entire function, if we just trace along here, that's at this point right here. Okay, so this local min is also an absolute or a global min. And it can be both. Okay, you can be a local min and a global min. But then the global max, well, our local max right here, this one is not the highest value on the function, right? There are several function values higher than it. But if we look at this endpoint up here, this one, if we compare its output to everything else, it is significantly higher than all other output values. So this one would be the global max. Okay. Now, when we look at the case with no endpoints, if we have no endpoints at all, then basically we don't have endpoints to look at when we're comparing. So we still look at all the local critical points, but then we're going to also look at the long-run behavior to determine if it is justified that there is an absolute max or min. So get another graph here. So similar to this last one, but this time the graph grows infinitely in both directions. It doesn't stop. So in this case, we still have our local min. We still have our local max. And we still have our local min down here. Now the absolute min, that remains unchanged, right? This point down here, this local min, is still the lowest point on the entire function. So this one is going to be local and the global min. Okay, that has not changed. However, now, when we look at the global maximum, well, this function, right, this local max is still not the highest point. There are lots of points on both sides that are higher than it. The problem is that this graph continues on forever towards positive infinity. So if I'm trying to find one highest point to be my absolute or my global maximum, there is not one. There is not one single point that is the highest. It'll just keep going and going forever and ever. So we can say this one has no global max. And that's just for this specific example. So let's go ahead and look at this example down here. So we have f of x equals x cubed minus 9x squared minus 48x plus 52. So this is the same function we've been working with, right, for quite a while now. So we've already found critical points to this. So we take f prime, we get 3x squared minus 18x minus 48. So we get our critical points at x equals -2 and 8. And then what we're going to do is we're going to evaluate f of x. Okay, so not the derivative. This is the original. We're evaluating the original function at the critical points and at the endpoints. Okay, and when we say we're evaluating the original function, we're doing that because we want to identify which of these has the highest output and which one has the lowest output. Okay, so highest value, lowest value. That's absolute max, absolute min. So if we do that, we find, so let's see here, critical points, f of -2 and f of 8. And then the endpoints, we have f of -5 and f of 14. Okay, this function can get pretty big, so these values are fairly large, but we get f of -2, that's 104. F of 8 is -396. F of -5 is -58. F of 14 is 360. So when we're looking at where the global max and global min are, well, the global max is just the highest output. So that one is this one right here. That one has the highest output. So our global max is at the point 14, 360. And the global min, whatever the smallest output is, that's right there. So our global min that's going to be at the point 8, negative 396. So that would be our global max and our global min for this function that we've been working with for several sections now. Now, one use of the concept of a global or absolute max or min is that oftentimes when we're working with real modeling problems, with real world contexts, we don't want to know that something is just the largest or smallest value in its immediate time frame or its immediate vicinity. I want to know what the absolute biggest or smallest value is for a function. So along those lines, we're going to look here at this biological example. So for time t greater than or equal to 0 in days, the rate at which photosynthesis takes place in the leaf of a plant, represented by the rate at which oxygen is produced, is approximated by this formula. So P of t is 100 times e to the negative 0.02 t minus e to the negative 0.1 t. When is photosynthesis occurring fastest, and what is that rate? Okay, so we're looking to determine when is photosynthesis occurring fastest. Now, when we say fastest, that's an important thing to note what we're actually looking for here. We're looking for the moment in time, the value of t, where the rate of photosynthesis is maximized. That's really what this is asking for. When is that rate of photosynthesis maximized? Okay. So, in order to do this, we first need to find the critical points. So let's do that first. So we get P prime of t. So the 100 is just a constant multiple. Just leave it out in the front there. Take the derivative, e to the negative 0.02 t. That's just, again, e to the negative 0.02 t times the derivative of the inner portion because of the chain rule. So that's times negative 0.02. So that's negative 0.02 e to the negative 0.02 t. And then minus the derivative e to the negative 0.1 t is again e to the negative 0.1 t times negative 0.1, right, the derivative of that inner portion. So that's plus 0.1 e to the negative 0.1 t. So then to find critical points, we take this first derivative and we set it equal to 0. So now our job becomes solving for the value of t, and that gives us our critical point, and then we'll go ahead and test it. So let's go ahead and just play around with this algebraically. So divide away the 100, right? It's just a constant. Just divide it away. So we get negative 0.02 e to the negative 0.02 t plus 0.1 e to the negative 0.1 t equals 0. I'm going to add this term over to the other side just so that I can be left with all positive things. So this is 0.1 e to the negative 0.1 t equals 0.02 e to the negative 0.02t. Okay. And now, solving this, we have to get a little creative algebraically with this. So what we're going to do is I'm going to need to get the e's on one side and the constants on the other. So I'm going to actually divide both sides of this. So I'm going to divide both sides by this e term and by this constant term. And once we have done that, what we're left with is e to the negative 0.1t over e to the negative 0.02t equals 0.02 over 0.1. Using the laws of exponents, this is going to give us e to the negative 0.08t equals 0.02 over 0.1, that's just 1/5. And we're getting so close to finding the t value. Now we need just to take the natural log of both sides. Oops. So take the natural log of both sides, we get negative 0.08t ln of e, right, which is 1, so it just goes away, equals ln of 1/5. ln of 1/5, if you want to do a little just side work over here, using the properties of the log, ln of 1/5, that's the same thing as ln of 1 minus ln of 5. ln of 1 is 0. So that's just negative ln of 5. We saw a similar argument to this when we did half-life, right, back in the previous chapter. So this gives us t equals negative ln of 5 over negative 0.08. So that's just ln of 5 over 0.08. That's our exact value. And then if we just approximate this, this is approximately 20.12. Okay. But this is just a critical point. Okay, so this is our critical point. However, we need to make sure that this is actually a max. So make sure this is a max. Because it's not a guarantee. And the fact that it's a critical point means it could be nothing. Right? We still need to test it to make sure. So we would test it using either of the derivative tests, first or second. So I used the second derivative test to get this one. So when you do the second derivative test, you just take the second derivative. Okay, so that's going to be the 100 still there. When you start multiplying those constants out in the front, you get negative 0.02 times another negative 0.02 because of the chain rule. So that's going to be positive 0.0004 times e to the negative 0.02 t, and then minus 0.01 e to the negative 0.1 t. And then to test this critical point, we just plug it in to the second derivative. So p double prime of ln of 5 over 0.08, which of course, to get any sort of accurate reading on this, we would need to use the technology. We get negative 0.107. But it doesn't really matter what the value is. It just matters that it's negative. And since it's negative, that means the graph is concave down, right? So it looks like this, which means our critical point is up here. Our critical point is a maximum value. Okay, so we can say, since t equals 20.12 is a local maximum, and it is the only critical point, it must be the global maximum. Okay. So what this is telling us, so since we know it's a local max and it is the only critical point, if it's the only critical point, that means that this graph cannot have a min, right? It cannot have a min. It can only go down. So basically, once it goes up, right, it hits its maximum value, it starts going down again. Once it starts going down, it will never go back up again. If it never goes back up again, that means this must be the highest value on the whole graph. That's why being the only critical point allows us to conclude that it is the global maximum. Okay. And then the rate itself, so P of ln of 5 over 0.08, that is approximately 53.5, so that we can answer the question in context, because we do need to answer these questions in context. So we can say, thus, photosynthesis occurs fastest after about 20 days, right, 20.12, and has a maximum rate of about 53.5 units of oxygen per day. So that would be our maximum occurring at about 20 days, and the maximum rate itself at about 53.5 units per day. All right. So let's shift gears here a little bit when we move into section 4.4, talking about the business and economics side of this max and min value, and just in general how we can use these derivatives to interpret results for cost, revenue, and profit. Okay, so just as a reminder, profit is equal to revenue minus cost. Marginal revenue, that's the derivative of revenue, R prime, and marginal cost is the derivative of cost, C prime. So given two graphs for R and C, estimate the maximum profit that's given by these graphs. So the graphs here, this one is R, that one's R, that one's C. Okay. The axes here, the horizontal axis is Q, quantity. Vertical axis is going to be dollars, and that's going to be in thousands. So that's in thousands of dollars. All right. So we need to determine where the maximum profit is. Okay, well, in order for profit to be maximized, since it's revenue minus cost, I need the point where revenue is going to be furthest away from cost that it could possibly be. So let's look on the graph here. So notice way down here, there's a bit of a gap right here, right? And right, that's pretty big as we get down here. However, the function that's on top is the cost, right? So this one actually would represent negative profit because the costs are higher than the revenue. So let's look in here for a minute. So notice as I'm down here, we have some good spacing for cost and revenue, right? But the largest difference between them really seems to be right about here. Right, it looks like somewhere in the middle there appears to be where that difference between them is the greatest. So when we're trying to identify where this maximum profit occurs, I would say it occurs at this value right here. Looks like about 15. Okay, and that difference, right, these are all just going to be rough estimates. Looks like we're going from about 21 up to 29, roughly. Okay, so this is a difference of 8,000. Okay, so our max profit of approximately $8,000 occurs when production or I should say quantity. Okay, it means the same thing, but I'll keep it with the Q. When quantity is 15 units. Okay, so and again, this is when the difference between revenue and cost is the greatest. Now, this is something, we didn't need any calculus for this, right? We're just looking at the difference between the graphs and when it's the biggest. But I want to look a little more in depth at what actually is happening at this optimized point that we're looking at here. So I'm going to have 3 points in question. So this one right here, that's going to be A. We're going to look at these points here. And then point B, right there. So we'll look at these points. And then point C, put somewhere up here. They don't need to be evenly spaced. These are just kind of arbitrary at this point. So those are the points in question. Okay. Now, what I want to do is I want to look at the behavior of the graphs, at the growth of the graphs. So this one was revenue, this one was cost. Now let's look at the slopes. Let's look at the growth of the graphs. So at the point A, there's a tangent line for the revenue function. There's a tangent line for the cost function. So at x equals A, if we're comparing marginal revenue to marginal cost, right, how much they're growing respective to each other, looking at the derivative, well, I would say that this one is growing faster than this one, right? So revenue is growing faster than cost at this point. So we say R prime is greater than C prime, right? So marginal revenue is greater than marginal cost. Now if we look at the point C, so we'll come back to the point B in just a minute. Look at the point C, at what's happening here. So in this situation, notice the revenue graph is still growing, but now the cost graph has a steeper incline at this point. So C prime is greater than R prime, right? So in this case, marginal cost is greater than marginal revenue. And at this point B, right, this one that we are looking at specifically, if I draw a tangent here, notice the rate of growth, or that rate of change of the two graphs at x equals b, they appear to be the same, right? It looks like C prime and R prime are equal to each other, or in other words, marginal cost equals marginal revenue. And it turns out this relationship is really what we're looking for here. So the general kind of rationale behind this is if we go too far, so if we're somewhere over here, where we've gone too far, well, now all of a sudden you might still be making more revenue than your cost, but if you keep going and push it too far, now your profit is declining, right? So notice that distance has declined. You've kind of cut into your profit margins a bit. Whereas if you stop too soon, right, you are still making a good profit here, but there's more that could be made, right? We want to get it to this maximum length up here. So you don't want to push it too far because then your costs will start catching up to your revenue. You don't want to stop too short because then you've kind of left extra money on the table that you could have made. So finding that maximum value is when marginal cost is equal to marginal revenue. So we can actually verify this. So like I just mentioned, this suggests maximum profit can occur when marginal cost equals marginal revenue. So now let's look at the profit function and let's find its critical points. So profit is revenue minus cost, right? So the derivative is going to be R prime minus C prime. And then to find the critical points, we set this equal to 0. Okay, add this one over to the other side. We get R prime of Q equals C prime of Q. And what are these, right? R prime, that's just marginal revenue, and C prime, that's just marginal cost. So this means that maximum or minimum profit can occur at these critical points when marginal revenue equals marginal cost, or possibly at endpoints. And we do need to check endpoints, but oftentimes we'll find that it is, in fact, at these critical points that we're looking at. So let's look at an example. So the total revenue and cost curves are given. So let me label these. So this one is revenue. This one is cost. And we want to sketch the marginal revenue and marginal cost, discuss the curves and significant points, and determine at which quantity is profit maximized, and then graph the profit function. So, to graph these for the marginal cost and the marginal revenue, well, let's look at slopes here. So, the marginal revenue, so revenue function is linear. Right? This is a line, so it has a constant slope. So if the slope was, 1, 2, whatever it may be, it's going to be that same output, that same value at all points on its graph. So marginal revenue is actually a constant function. It's just a horizontal line. So that's marginal revenue. And then marginal cost, so if you look at kind of the behavior of it, right, the slopes are pretty positive. They get smaller and smaller, heading towards 0, and then they start growing again, right, as we get higher and higher. So they start off really positive, get closer and closer to 0, and then they get more positive again. And this would be our graph for marginal cost. And our points of interest here are going to be these points of intersection of the two graphs. So I'm going to call those Q1 and Q2. So let's look at what's really happening at Q1 and Q2. Okay, so we're going to discuss these significant points and determine where our profit is maximized. So on this curve here, so at Q1 and Q2, at Q1 and Q2, marginal cost equals marginal revenue. So that tells us these are the critical points, right, on the original graph. So the question is, what's happening at these critical points? Well, to the left, so to the left of Q1, what is profit doing? So we would say that profit is decreasing. Is decreasing. And increasing to the right of Q1. Right? So think about it. Right? Marginal cost to the left of Q1, marginal cost is larger than marginal revenue. So that means profit is dropping. But once we get past Q1, now all of a sudden marginal revenue is greater than marginal cost. So that means that profit is now increasing. So we went from decreasing to increasing. Okay. So Q1 is a min. It's a minimum value. Now, via similar reasoning, marginal revenue greater than marginal cost to the left of Q2. So profit is increasing to the left of Q2 and decreasing to the right of Q2, right? Because marginal cost then gets larger than marginal revenue at that point. So we can say profit is increasing left of Q2, decreasing right of Q2. So Q2 is a max because we go from increasing to decreasing. So then we wonder, is this the global maximum value? Well, if we look at the endpoints tell us, just by looking at the original graph, that cost is greater than revenue at both endpoints, which means that profit has to be negative, right? So profit is negative at the endpoints. So maximum profit must occur at Q2. So we have maximum profit occurring at Q2. So that is our global maximum, right? And if you look at the original graph, hopefully that would kind of make sense. So what we have here, right, these 2 points, Q1 and Q2, look like they occur right about here and here, right? It's about Q1, about Q2 right there. So that would match with what we saw in the previous graph. Now, if we graph the profit function, profit starts out negative. So somewhere down here, starts out negative. It hits a minimum at Q1. And then it starts growing. That's the point where they cross each other. Now you're actually making profit. And then it hits its maximum over here at Q2. Oops. Sorry, everybody. There we go. So over here at Q2, that's where we're going to get our maximum profit. Right? This is on our Q axis, on our dollar axis up here. So this would be a graph of the profit function. Right? So pi of Q. All right. So that's a lot of graph interpretation. So now let's look at a more numerical example. So find the quantity which maximizes profit if R of Q equals 5Q minus 0.003 Q squared, and the cost function is 300 plus 1.1 Q, where Q is quantity from 0 to 1,000 units, and we're wondering what production level gives the minimum profit. So we need to, first off, find where marginal cost equals marginal revenue. Okay, so we need to get marginal cost and marginal revenue. So marginal cost, that's C prime of Q. That's just going to be 1.1. And marginal revenue, that's R prime of Q. That's going to be 5 minus 0.006 Q. So if we set these equal to each other, so 5 minus 0.006 Q equals 1.1. We get 0.006 Q equals 3.9. So we get Q equals 650. So this is where marginal cost equals marginal revenue. So the question now, is this a max or a min? Okay, that's the next big question. So let's check to the left and to the right of 650. So that's kind of our first portion here. So we're going to check to the left and right of Q equals 650. To see what the functions do there. So if we check r prime of 649, that value is approximately 1.106. If we compare that to C prime of 649, well, C prime of anything is just going to be 1.1, right, or 1.10 if you want. So that means R prime is bigger than C prime. And then if we compare past 650, so R prime of 651, then we see that R prime of 651 is 1.094, and C prime of 651, again, is unchanged, it's just 1.1. So this time, C prime is actually larger. Okay, so what does this tell us? So profit, if we went from marginal cost being greater to then marginal cost being less, right, to marginal, did I say that backwards? Marginal revenue being greater to marginal cost being greater. So if we make that switch, profit goes from increasing to decreasing at Q equals 650. Thus, 650 is a maximum. And I think in the problem, yeah, if back up here in the problem, it says we want the production level that minimizes the profit. I think that's just a typo. I think, why would you want to minimize your profit? I think that should be maximum. Okay. So 650 is a maximum. But the question is now, is it a global max? Okay, so is it the absolute biggest value that they could have for profit? And that's something that you want to know, right? Because if you say, oh, well, it's a maximum value, the company would say, great, that's wonderful. And then you say, oh, but it's not the absolute max. You could have made more money somewhere else. Well, actually, I want to know that, right, if I'm trying to make profit. So we need to also check the endpoints. Because remember, the global or absolute max can occur at either the critical points, which we found 650, or at the endpoints. So the endpoints, if we go back up to the problem here, this is from Q going from 0 to 1,000. So we're going to need to check at 0 and check at 1,000. So at Q equals 0, the profit at 0, if you take revenue minus cost, plug in 0, you end up getting out negative 300. So I can tell you that that's probably not going to be the global maximum. At Q equals 1,000, our other endpoint, our profit function at 1,000 is 600. And then at our critical point, so at Q equals 650, so comparing outputs here, profit at 650 is 967.50. So we can see, of course, that is the largest value out of all of these. So when it comes to making our conclusion, we can say thus the maximum profit of $967.50 occurs at a production of 650 units, and the minimum profit, in case you were wondering, right, because I guess the question did kind of ask about the minimum profit, the minimum profit of negative $300 occurs at a production of 0 units. Which hopefully makes sense, right? That if you haven't made anything, then you're not going to have a very big profit because you have those overhead costs, right? Those fixed costs, but no revenue yet. So your minimum profit in this case is going to occur at a production of 0 units. Okay, so this is the concept of the global max, the global min, being tied into this business economics example, this modeling problem. So you see that we can use all of these applications here and start applying the concepts of the local minimum and the maximum, the global min and max, and start looking in the context of cost, revenue, and profit.